Recording is rolling. It is Tuesday, October 1st. I have a starter question here. Classic Atwood. Hey, this looks like your guys' lab yesterday. Suppose I have 2 kilograms and 3 kilograms, double elevator classic Atwood. What is the acceleration of the system? And then a follow-up question. Hey, I wonder what is the tension in the string? Shouldn't have you guys address so much yesterday, but maybe we can figure that out too. All right, then after we do this one, we're gonna hit your guys' chapter 4 or 5 puzzles. It's right here. And we did some of these the other day, and we're gonna just continue this adventure, solve some more of these. All right, your guys' forces quiz. I did finish writing this last night. I'm gonna get this to you guys by the end of class Thursday, I think. So we'll take a few more days to solve more puzzles, do some more lab activities. Let's have the puzzles and quiz both due on Monday the 7th. Okay, so these puzzles we've been solving, and we're going to solve more today, and we'll solve more later this week. Right? And also the quiz that I'll get you guys on Thursday. You can turn all that in on Monday, unless you finish it early. Turn it in early, it's a good thing. All right, so you guys get okay with the setup, what we're doing? All right, so first question, that Atwood right there, 2 kilograms versus 3 kilograms. Okay. What's the, I've seen this phrase different ways. I've seen this, what's the acceleration of the whole system? Right, which is, I'm gonna actually approach it. See, what's the downward acceleration of the large block? Or what's the upward acceleration of the small block? Of course, those are all the same answer. Okay. So what's the acceleration? After we get that, we'll switch over and find out what's the tension. Okay. Give you guys an opportunity to possibly solve that first. All right. Does anybody know what is the acceleration? Here's what, if you're working on that, here. I'll walk you guys through this a bit. So I have a couple of posters on Atwoods, and they're a little bit different design. Right, so back on Friday, you guys were doing the modified Atwood, and then I debriefed that with you guys. Right, and then yesterday, you guys were doing this classic Atwood, and I had you guys turn this in, but I hadn't actually gone over the answer with you guys, right, as to what is the acceleration. So yeah, let's do all that now, and then we'll try out that example question. Okay, so these are different setups. They have slightly different answers, but they start out kind of the same way with Newton's second law of motion. You guys see this pink box is the same for both, right? Showing both of them, so you can kind of compare and contrast, right? So here's super generic Newton's second law of motion, but it applies a little bit differently to each one. Now, there's different approaches you can take to solve these Atwoods. I like to do what's called a whole system approach. I treat the 2 blocks tied together as like an entire system. Okay? And from that point of view, the acceleration is, well, what is the net force and what's the total mass, and just divide those two, net force and total mass. Now, for the modified Atwood, it turned out, you guys remember this from the other day, the net force was the hanging weight. There were a bunch of other forces, but they were either internal to the system or canceled out, so they didn't count towards the net external force. Okay? Okay. Now, the lab you guys did yesterday, it's really a competition between these 2 weights, right? Like one of these weights says, let's go clockwise, and the other one says, no, let's go counterclockwise. It's like a tug of war. Do you guys remember? Here, as one example, as one boundary condition, you may have tried this yourself yesterday too, is what if the 2 weights were the same? Guys, what if you put like 2 newtons weight here and 2 newtons weight here? What did the system do? Did it even move? No, you start from rest and it didn't even move. So, okay, maybe that's a hint that would zero out somehow. Hey, maybe they're subtracting from a systems point of view. That's what I have here for the net force. You guys see I got the difference in weights, right? And the total inertia moved around, the total mass is, well, that's the sum of the masses. It's moving both these blocks. Now, different directions, one's going down, one's going up, but that's okay, right? They're both moving the same, they're both accelerating the same, just different directions, same magnitude. Right? Actually, this gold box right here is the answer I was looking for in your lab. Yesterday, at the bottom of your lab paper, it said A equals. I was setting up an equation, A equals. I want to see if you guys can figure that out. Right? Now, you guys approached it empirically, tested all different combinations of masses, starting from rest, move so far in so much time, you could calculate the acceleration, see if you can figure this out. But this is the answer. Right? So it's difference in weight over sum of masses. Right? Now, once you got the acceleration, you can go the next step and figure out what is the tension. And to figure out the tension, you either want to focus on only that block or only that block. You can pick either one. And I have a green equation for each one of them. Now, they're both Newton's second law of motion, but Newton's second law of motion, but they only apply to one or the other block. So like this mass 1, it's got tension up and weight down. That could be the net force there, driving mass times acceleration for block 1. Or from the perspective of block 2, I got weight down minus the tension up. And that's the net force driving block 2 to accelerate. Right? Last word here before I flip over and start solving it is some physics textbooks, some instructor. So if you take physics in college, sometimes they like to, they might prefer to start with this system of equations, start with these 2 green boxes and solve it that way. Now, if you solve it that way, there would be 2 unknown values starting out. Okay, so what would you know? What would you not know? Maybe you know what are the masses M1 and 2, you know the gravity field. Normally, you know those things. You're trying to solve for what's the acceleration, what's the tension. Okay, so you have 2 equations, 2 unknowns. You could solve it that way. Okay. Now, I'm going to take you guys through the whole systems approach that I tend to prefer to do myself. Let's try that. All right, so guys, before I go solving this, did anybody figure out by now what is the acceleration of the system? 2 kilograms versus 3 kilograms. Does anybody know? Yeah, what you got? Okay, yeah, that sounds right. That sounds right. Great. I'm going to round that a little bit to, okay, you said 1.96 meters per second squared. Great. When I solve it, I'm going to get about 2 meters per second squared. Going to round it a little bit. Yeah, sounds right. Did you also happen to get the tension? Not quite yet. Okay, yeah, I'm sure if I gave you guys a little more time, you could get the tension too. So let's get going on this thing. So here you guys go. First here, taking some notes would be good. So I got 2 blocks. Let's call this guy 3 kilograms. Let's call this guy 2 kilograms. Boom, boom. Got some masses on the board. Okay. Let's do a free body diagram. Okay. Get some forces. So I think this 3 kilograms weighs approximately how many newtons? How do you go from mass to weight? Multiply by gravity field, right? mg. Right? If I round gravity field to about 10 meters per second squared, how many newtons weight is that? So like 30 newtons, right? Like 10 kilograms, 3 kilograms weighs 30 newtons about on Earth. Right? Okay, if that's 30 newtons, how much does 2 kilograms weigh? About 20 newtons. Right? And I'm making a deal about this so that you can scale these correctly. Right? Like here, I think it might be pretty close. Oh, guys, if I drew these proportionally correctly, should 20 newtons to 30 newtons, should the length of the arrows also be like a 2 to 3 ratio? You guys think? I tried to draw it pretty close to that. Okay. Good so far? Okay. Now, those forces right there are the most important forces. Those are the external forces. You can actually use this right now to solve for acceleration of the system. Okay. But I am going to go back and add a little bit more to this story. There's also a tension in the string that is acting on each of the blocks. Guys, is it the same tension everywhere? Same tension? Yeah. So this one string has one tension. I give this pulley here as massless frictionless. Pretty close to true. Yeah, I think this one string has one tension in it. Yeah, guys, if this is going to accelerate clockwise, you guys do see it's going to accelerate overall clockwise, right? Clockwise, right? The large block is going to be moving down overall. The small block is going to be moving up overall. In fact, they'll be accelerating that way. There should be a net force in each of those respective directions. Okay? So what I'm trying to get at is, how does the tension force compare to each of these weights? What do you guys think? Is the tension less than 20, between 20 and 30, or more than 30 newtons? What does the tension have to be? Between 20 and 30 newtons. Yeah, right. I think the tension has to be more than 20 newtons because it has to, there has to be an overall net force pulling 2 kilograms upwards. I'll call this F sub T for the tension force. And we're going to eventually solve for that. Okay. I think the exact same tension force has to act over here on this block, but it's going to be less than 30 newtons. So that there's an overall net force pulling the 3 kilogram block downward. You guess that too? Okay. Now, we don't know what that tension force is yet, but I know it's somewhere between 20 and 30 newtons. I'm going to guess maybe about 25-ish. It's probably not exactly 25, but it's probably pretty close. You guys think? Okay. All right, let's do Newton's second law of motion. Acceleration equals net force divided by mass. It will say total mass. That, okay. This is Newton's second law of motion. Newton's second law of motion, right there. All right, so say acceleration equals a fraction bar. Right? Now remember, the tension force is just internal to the two block system. I'm doing this like a whole system perspective approach. Okay? The tension is internal. These two weights are the external forces that are actually driving the system, and they're competing with each other. So what should I put in this numerator right here? So it goes right here. It's like that, right? So could that be 30 newtons saying, let's go clockwise, minus the 20 newtons holding it back saying, no, I want to go counterclockwise. Is that true? Right, just like that. Right. And guess how much mass is being moved around? Ah, you gotta see 5 kilograms, 5 kilograms. Right? So you got the 3 kilograms from here and the 2 kilograms from here. I'm gonna add that all together. Right? Remember, mass is a scalar quantity. Mass does not have a spatial direction to it. Right? It's just some total inertia in this case. Do you guys see I'm gonna have 10 Newton net force acting on 5 kilograms? Right? Aha, here we go. Divide that out. 10 over 5 is 2. And guys, newtons divided by kilograms is what unit? Meters per second squared, which describes an acceleration, doesn't it? There you go. There's your first answer right there. Okay. Right, so you could say the acceleration as a whole is 2 meters per second squared. The large block is accelerating down at 2 meters per second squared. The small block is accelerating up at 2 meters per second squared. But they're all tied together. They all have the same type motion. Just one's down, one's up. Right? All good. All right. Now we're going to switch over and solve for tension, or maybe somebody already knows what is the tension. Did anybody solve at this point? What is the tension exactly in that string? What you got? About 24 newtons? Yeah, that sounds right. Sounds right. All right. Okay. Exactly. He's getting these. Right. So remember, I was telling you guys that you can focus on one or the other block, and each of these green boxes is, well, one or the other block. It's Newton's second law of motion as it applies to one or the other block. Right? So what I'm going to do this is split my paper and solve it each way and show you guys that it's the same thing no matter how you approach it. So I'll do point of view 2 kilogram block, and then point of view 3 kilogram block. Right? Try it once each way. Okay? So from the perspective of this 2 kilogram block, oh, and here's my framework. Newton's second law of motion, net force equals mass times acceleration. Okay? Look at that. Okay? The net force on the 2 kilogram block, you guys see some tension's pulling up and its weight's pulling down? Yeah, I can just do that. The tension up minus the weight down. Put the unit right there. Okay. That's driving this 2 kilogram block. That's the mass. Bing, right there, 2 kilograms to accelerate at how much? How much is it going to accelerate up? 2 meters per second squared. Right there. Meters per second squared. It's it. 2 kilograms times 2 meters per second squared. That gives you what? For what? What's the unit? Newtons, 4 newtons. Kilogram meter per second squared. That's a newton of force. Right? Guys, 4 newtons here plus 20 newtons here gives you what? 24 newtons. Oh yeah, exactly what Zach was saying. 24 newtons. All right. Right. Hey, I wonder if we did the perspective of the 3 kilogram block, if we should get exactly the same value for the tension force. Let's say we do. Right, so got net force equals mass times acceleration, so before. Okay. Now this time, the overall net force is down. I'm going to call it down positive. But what we did so far, maybe up is positive, but now I'm going to call it down positive. I'll do 30 newtons down, 30 newtons down, minus the tension pulling back the other way. Right? Since it's also accelerating down, now acceleration can still be positive, so that's helpful. Okay. Now it's a 3 kilogram block, accelerating down at how much? 2 meters per second squared. Right? Ding, ding. All right, all good? All right. 3 times 2, that's 6. And then kilogram meter per second squared, that's newtons. Is this 6 newtons right here? 6 newtons. All right. Now I can subtract that over here, add the tension force over here. The tension force is what is 30 minus 6? 24, and that's of course newtons. Hey, it's the same thing. Oh yeah, oh yeah. Ding. Right there, 24 newtons, no matter how you solve it. All right, all good, all good. Okay. All right, all on one page. All right, so back up, gonna go over this. You guys want we're like forest for the trees. How do you solve these things, right? So there's 2 main approaches. The approach I like to do, which I did right here, is first start full system, say, hey, what's the acceleration? Well, it's the net external force, so the difference of the weights acting on some total mass, just add the masses together. Right? They'll tell you the acceleration of the system. Right? And then you can dive a bit more granular and say, well, pick your favorite block and set up Newton's second law of motion as it applies to that block, and you can solve for the tension. And we did both of them, of course, they're the same tension. Right? So it's going from here to here to, well, either one of these. Right? Right. The other way to approach these Atwoods is, and I'm saying this especially because you might take a physics class in college and they might do it this way, is to actually start with these 2 green boxes. Say, what's going on with this block? What's going on with this block? Now, if you do that, you'll have 2 equations with 2 unknowns. You won't know the tension force, you won't know the acceleration. But you could use, say, a substitution method, for example, and then kind of get them both at the same time. First, you get the same answer. All right. All right, you guys get on Atwoods so far? All right. All right, so textbook time. So the other day, we solved these 3, which they were all multi-part questions, so we solved like a bunch of different questions. We're moving on to, here's what I've been able to do today. We got 74 car racing, there's an 82 jet, and then there's this one in the middle, number 60 skating, and then we have like a minute left over in class, so I just call it a wrap right there. All right, so I think that's our goal today. After today, we got 3 more days this school week. I'd like to take at least a day to solve more puzzles, and then there's a couple of labs and lab activities I want to do also, so if I can fit those in. All right, 74, car racing. A race car has mass 710 kilograms. All right, 710 kilogram mass. It starts from rest. It travels 40 meters in 3 seconds. Ooh, now pause right there, because a lot of times you can get, say, like halfway through a physics question and you can kind of see where they're going with it. I got a poster already that I'm thinking in my mind. There we go. I'm thinking this already. You guys remember this bridge poster? The bridge poster? All right. So do you guys notice? I haven't even finished reading the question yet. You guys notice they already gave us 3 kinematic values? Guys, if they gave you 3 kinematic values, do you think you could maybe pick a kinematic equation and solve for acceleration? They did also give you the mass of the car. Do you guys think that a really good opportune question might be something about net force? They gave you 3 kinematic values. You can pick one of these equations and solve for acceleration. They gave you the mass of the car, F equals ma, and get the net force, right? Or maybe that's not what they asked, but that could definitely be an opportune question. Let's read the rest of this thing. What else we got? The car is uniformly accelerated during the entire time, which even if they didn't say that, you would assume that for this class. That's always the case for this class. Uniform acceleration, great. Question, what is the net force exerted on it? If that's exactly the way they went with that. All right, saw that coming. Right. So 74. Okay. Let's do, we'll do the full thing. Like, obviously we're gonna need some equations and whatnot, but I wanna make a free body diagram also. So let's get a car going. I guess I have a turtle looking race car. And let's think a free body diagram on this car. Say he's trying to move overall to the right. Okay, so right with velocity. No, of course, that's not a constant velocity. He's speeding up, he's accelerating. Okay, so his velocity is always changing, but let's just have him going to the right. Okay, let's do free body diagram, FBD. Guys, what's one force acting on this car? Yeah, how about his weight? So call it mg. In fact, if you want, you could tag a number to that too. They say it was 710 kilograms. So would that be 7,100 newtons if you like? Right. What's oh wait, but it's not in free fall. What's holding it up? Normal force, F sub n. That's exactly balancing it out, isn't it? Right? Next force. Well, I mean, if it's accelerating, there's got to be something else going on. So there's a net force, right? Oh, guys, if the car is accelerating forward, maybe it's moving forward faster, it's accelerating forward. Which way do you think I should draw a force to accelerate it forward? Should it be a forward acting force? Maybe something like this, for example, right? And I need to label that force. Because what force is actually allowing the car to accelerate on a flat road? Huh? Friction. It is a friction force, right? Yeah. We get here. Think about it this way: is what if there was no friction? What if the road was iced over? Or what if it's like really muddy and the wheels are just spinning in place? Can't gain any traction. Can't move at all. It's just kind of stuck there, right? Yeah. But if you have a dry road, now it's a lot easier to zoom. Now you can definitely accelerate forward, right? Oh, I've seen the question come up like, hold on a minute. I thought friction always opposed the motion. So if the car's trying to move forward, how can friction be propelling forward if it's going forward? But guys, think about which way the wheel is actually spinning. Okay? So yeah, let's take it back to like either an icy or a muddy road where it's just spinning in place. Do you guys see that wheel just spinning in place right there? Right now, I see it spinning clockwise. You guys see it going clockwise because the car's trying to move forward. That's wheel spinning clockwise. The top of the wheel is going definitely to the right. But what about the bottom of the wheel? Guys, the bottom of the wheel is actually trying to turn which way? To the left. Whoa, right? That's what clockwise is. It's to the right on top and it's bottom to the left on the bottom. Yeah, so this friction force actually is opposing that, and that's allowing the car to move. All right, so that was a little extra. All right, so what they give us? Let's get some numbers on the board here. They told us mass of the car is 710 kilograms. They told us what else we got? Car starts from rest. V naught is 0 meters per second. It goes 40 meters in 3 seconds. Okay. They gave us at least 2 digits on each of those numbers. Sometimes 3. Looks like we got 3 digits of precision on the distance, only 2 digits on the time. Right. So, all right, fine. Just thinking ahead to the end of this question, I might ask you guys a question about significant digits. Right? These are all given values. Maybe you could also assume the gravity field of the planet if you like that too, something like that. All right. So you guys good? All right. So you guys remember I gave you guys a roadmap for this one. I said it gave us 3 kinematic variables. Maybe we can solve something over here. Get what is the acceleration of the car, and then flip over to Newton's second law of motion to get the net force, which in this case is going to be the friction force. Okay? So which formula? You guys remember those 3 kinematic formulas? Which one is going to allow you to solve for acceleration? Ask the same question in a different way. Which is the only kinematic formula that has both distance and time in it? There's only one of them. Which one is it? First one. Aha. This is like x equals v naught t plus 1/2 at squared. Looks like that. Okay. Now that's the full version. But you know what? If it starts from rest, can you just goes away? Okay. Because now we just got x is 1/2 at squared. Right? Okay, so anything that starts from rest, x equals 1/2 at squared. Okay. All right. Now here's where we're solving for acceleration. I guess I got an option. Probably want to finish this off. Let me go ahead and split my paper. You don't have to do both ways. I'm going to do both ways. You could do variables, or you could do, I'll say, numerical values, something like that. All right. So in terms of variables, say so x is 1/2 at squared. Solve for acceleration. I can cross multiply the 2, divide down the t squared. acceleration is going to be 2x on t squared. Now, if I plugged in my numbers first, x could be 40 meters equals 1/2 acceleration we're solving for. The time was 3 seconds to get there, and that's being squared. So it'd be acceleration would be 40 meters times this 2, all divided by 3 seconds being squared. Is that right? There's variables. There it is with the numbers plugged in. Which, yeah, it does look a heck of a lot like this one right here, doesn't it? Right, this is the first kinematic formula in disguise. V naught was 0, 2x on t squared. Okay. All right. I think you guys did that as part of your Atwood lab recently too, right? Started from rest, moved some distance, some stopwatch time. You guys did that. All right, let's get a number right here. Get a number. Got 80 over 9. Acceleration is, the number on my calculator screen says 8.88888. Okay, so something like that. And what unit? Guys, that's 8.89 what? Meters per second squared. Aha. Right. Now that's not the answer yet, but that is an important halfway point on this question. So I'm going to circle that. Right, so now we know how much is the car accelerating. Okay. You guys see on our Forest for the Trees roadmap, we're crossing this bridge. We're like halfway across this bridge right now. Right. So started here, we're halfway here. Right. Working our way over to Newton's second law of motion. All right, are we good? All right. I got some other questions about this. Here, how about this? How about this? Okay, suppose you're riding in that car. You're riding in that car. How many G's does this feel pretty close to? Is that almost 1 Earth acceleration worth of horizontal acceleration? I think it is. That's almost 1 G. Woo! You're really throwing back in your seat there. Okay. I got another question about this too, but I'm gonna maybe circle back to that later. Let's go ahead and finish this out first. We got to figure out what's the net force, the friction force on this car. All right, you guys ready to do that? All right. So net force equals mass times acceleration. The net force in this case just is the friction force. The vertical force is canceled out. The mass of the car was 710 kilograms. The acceleration we just found is 8.89 meters per second squared. Put it all together, 710 times 8.8. I'm getting the friction force is 6311. What's the unit? Newtons. That is the answer they're looking for. Here, let's go a few more steps with this. Right? You guys remember in the beginning, they gave you a bunch of given values. And they gave you at least 2 digits, sometimes 3 digits on the numbers, right? A general rule of thumb, especially if you're just straight multiplying and dividing, is that by the time you get your answer, the amount of precision you know can only be as much as the given values that you started with, right? So do I really know this 6,311 newtons? Do I know all the way down to that last digit? Probably not. Math gets kind of fuzzy at that point, right? How much could I say for certain I know? Let's do scientific notation. Can you guys write this number in scientific notation? 6.3. Right. And tell you what, if we only know 2 digits of precision, that's probably as much as I can reasonably know. Times what? 10 to the 3 newtons, just like that. Right. Oh, could I also call that 6.3 kilonewtons if I like? Right. So actually, any of those answers are good right there. Right. Guys good? All right. Now, I said I wanted to circle back to that acceleration of the car, which is allowed by a friction force, right? Isn't that friction force causing the car to accelerate, right? Remember I was saying, what if you had like an iced over road versus a dry road? On dry road, isn't it easier to do that? Especially, guys, this acceleration is probably as large as you can reasonably get out on the road. So you probably can't do too much more of that. And I don't know if it rained outside, you might not even be able to do that. So maybe the question I'm trying to trigger here is, what is the minimum coefficient of friction between the tires and the road to even allow any of this to happen? Okay. So let's do, you guys remember this coefficient of friction here? Looks something like this, right? Now, guys, if we're talking about a car gaining traction against the road, does that sound more kinetic, like it's sliding, or static, like it's sticking? What does it sound more like? Like probably static, you guys think, right? Which looks like this inequality, but here's what we're gonna do. I'm gonna say what is the minimum necessary coefficient of friction, and then I can make this an equal sign. Okay, right? You guys get that? And also I'm gonna rearrange this a little bit. Can I take the normal force and cross multiply that over here? Right. So it's gonna look like this. Friction force is equal to coefficient of static friction minimum times the normal force. Right. And if you think back to the free body diagram, isn't the normal force just exactly balancing out the weight? So it's the same magnitude. So could this right here be like 7,100 newtons? Because 710 kilograms weighs 7,100 newtons. And this friction force, we just found that. That's like 6,311 newtons. Oh, go ahead and keep those extra digits, just round after the fact. Okay. Hey, can I just divide this down? I get the coefficient of static friction minimum is, whatever that ratio is, 6,311 on 7,100. I'm looking at, hey, look at this, 0.8888. Huh. Right. Oh, guys, what's the unit on coefficient of friction? Newton per Newton, right? Or you could just leave it blank. Right? That's one of the rare times in this class you can just have a number. Right? Huh. That almost rings a bell. That almost looks like the acceleration, except that it's off by a factor of g. Right? G is 10 meters per second squared. Right? Very good. Okay, you guys see that? Okay. Which, by the way, is a poster that you already have. I'm gonna show this to you guys because this is going to show up a few weeks later in this class. Right? You guys remember a car brakes to a stop? Here's Newton's second law of motion. All right, here's the net force. Here's friction force substituted. By the time you work your way down to the end, here's how much the car is allowed to slow down braking to a stop. It has to do with the coefficient of friction between the tires of the road. Just simply multiply by the gravity field of the planet. Hey, doesn't that look almost exactly like what we have right here? The only difference is the car is speeding up. So you just take this friction force and just reverse it to make it speed up. Otherwise, it's the same thing. Okay. We got 0.888 times 10 is 8.888. Ah, guess that, meters per second squared. Right? Guys, here's another question. When you're working down, there's a variable that cancels out by the time you get to the end. What variable canceled out? The mass of the car. Guess the mass of the car has nothing to do with the rate that it can, in this case, slow down, or in the textbook, speed up. Right? So hold on to that idea, because a few weeks from now, when we're doing conservation of energy specifically, there's going to be a very similar question. We're going to use a completely different method to solve this. To say, how far does it take for the car to brake? Right? And again, the mass of the car is going to cancel out. I want to show you guys that that's true from this perspective also. Okay? By the time we get there. All right. You guys ready for our next one? What we got next? We're up here. Jet. It's 82 jet time. 82 jet. A 2.75 times 10 to the 6 Newton catapult jet plane. All right, pause right there. Oh, is that scientific notation? Right. Okay, 10 to the 6. That's a factor of a what? Is that 1,000, a million, a billion? What is that? A million. Aha. Can I call it like 2.75 million Newton? Oh, notice guys, newtons. Are they telling you the mass or the weight of that plane? What's measured in newtons? Is that a weight? I think it's a weight. Okay, so I'm going to file that away. I might want to get the mass later, but they gave us the weight. Okay. Is ready for takeoff. The jet's engines supply a constant thrust force of 6.35 million newtons. How much runway will it need to reach its minimum takeoff speed of 285 kilometers per hour? All right, I see all those puzzle pieces lying around. Yeah, I'm thinking how to put this together. So they gave you the weight of the plane. Do you think you could probably very quickly find the mass? Just divide by the gravity field, get the mass in kilograms. Okay. They gave you a thrust force. If you know the thrust force and you know the mass, which we're about to find out, can you solve for the acceleration of the plane? And if you know the acceleration and it starts from rest, and you're trying to get up to the speed and you want a distance, does that sound kinematic? Guys, here's the roadmap for this one. Here's your thrust force. The thrust force is going to be the net force, maybe driving it horizontally. Okay. Now, they did not directly give you the mass of the plane, but we can probably figure that out pretty quickly because they gave you the weight of the plane. So that'll let you figure out what is the acceleration of the plane. Once you know the acceleration, you can cross this bridge and say, well, if it starts from rest and you need to pick up to some minimum takeoff speed, you can solve for the runway distance. That's it right there. Boom, cross the bridge, boom, solve for X. That's it. That's the entire roadmap. Okay. All right, let's figure this out. There's a bunch of little things along the way. Yeah, we got to figure out the mass of the plane. Also, did you guys notice the units on that speed, that takeoff speed? Kilometers per hour, 285 kilometers per hour. Have we ever used kilometers per hour in this class? I don't think so. So if we go plugging and chugging in equations, you don't want kilometers per hour. You want what unit? Meters per second. So we're gonna have to do a conversion there too. Okay, so we got to figure out those things. Let's figure all that out. I got this jet plane accelerating. Here, I'll just start writing some stuff down. Well, let's figure out the mass first. Is mass just equal to the weight divided by the gravity field? Can we do that? Right. So let's take the weight, which was sorry, wrong one. Or forget that. Right. 2.75 million newtons. Divide by the gravity field of the plane. I'm going to round it 10 meters per second squared. Is that right? Okay. That could be the mass of the plane. Could that be 275,000 kilograms mass? Just like that? Is it? Okay. Also, the speed, I'll call it VF, V final, because it's speeding up until it reaches this takeoff speed, minimum takeoff speed. They gave us 285 kilometers per hour. And you guys told me we're looking for meters per second, right? Meters per second. Should I maybe set up some railroad tracks and do a conversion right here? Right, you guys think? I'm trying to convert from kilometers per hour to meters per second, so I have something I can plug in those equations with a calculator. So one step at a time. It's how many kilometers, or sorry, other way. How many meters are in 1 kilometer? Kilo is a factor of 1,000, right? 1,000. Right? So should the number 1,000 go on top or on bottom? 1,000 meters in 1 kilometer. Okay, now I have meters per hour. Okay, so I'm a step closer. I want meters per second. Let's go through minutes. How many minutes in an hour? 60. Should the number 60 go on top or on bottom? Bottom. 60 minutes equivalent to 1 hour. You guys remember how this process works, the theory, right? I'm just multiplying by the ratio that's just equal to 1. It's just swapping out the units. Whoops, this is out of charge. Okay. Now I have meters per minute. I want meters per second. How many seconds in a minute? 60. Now look at the units left on the board. Meters per second. Let's put it all together. Right, calculator time. So take my 285 kilometers per hour times 1,000 over 3,600. I'm looking at 79.17. That's meters per second. Now, realistically, that's too much precision. That's okay. I'll save my rounding for the end. Okay. All right. Okay. So let's get all our known values at this point. We did a little bit of solving here, a little bit of conversion here. So we did a little bit of work. Let's put it all on the board. So here's what I know. I know the mass of this jet is 275,000 kilograms. I know the thrust force, which is going to be the net force, is here, I'll write out the number full just so you get a different perspective on it. 6 million something newtons thrust force. I know V naught is 0 meters per second. I know the final, the takeoff speed, better be 79.17 meters per second. And all right, I think that'll do it for us. here's your given values. By the way, maybe like here's the plane, maybe. Right. On a runway, do a quick free body diagram. It maybe looks something like this. It's got a weight. It's got a normal force, right? Possibly starting to lift, maybe as it's going along runway. I'll just kind of incorporate that into that anyway. Right? This thrust force, 6 million newtons compared to the weight. Do you guys see the thrust force is like approximately 3 times the weight? Woo! Okay, so I'll try to draw it to scale that way. Up thrust. There you go. I bet the free body diagram looks roughly like that. Okay, and the thrust force would be the net force. All right, you guys good to go? All right, so do a little bit of work here, do a little bit of conversion, right, and we're going to get to this point. Right now, I think we're ready to go on this adventure. You guys ready? Right. So you know the thrust force is the net force. We figured out the mass of the plane. Can you figure out the acceleration? Once you got the acceleration, we're going to go over here and figure out the runway distance. All that right here. Okay. Let me fix this thing over here. Ooh. All right. All right. So, guys, what's the next equation I'm going to write right here? What's the next equation? Newton's second law of motion. There's Newton's second law. Okay. What goes in for the thrust force? 6 million something newtons. There's the thrust force from the engines. It's acting on the mass of the plane is this many kilograms. Right? Let's get a value here. 635. Oh. Give myself a little calculator work. Okay. Looks like 23.09, 23.1 meters per second squared. Okay. Now, pause right here. When you're solving physics puzzles, it's good to pause from time to time, make sure you're on track, your numbers making sense. Guys, if you were riding inside that jet, how much acceleration is that? Like how many G's? How many G's is that about? How much is 1 G? How many meters per second squared? About 10, right? And this is like 23 meters per second squared. Whoa, is that like almost 2.5 G's? Whoa, and that's just probably horizontal acceleration, right? If you feel sitting in that seat, you're really pushed back in your chair like, whoa, right? I don't think this is a commercial jet. I think this is maybe something military. They said like a catapult jet or something, right? So yeah, this is crazy bonkers acceleration here. I mean, it's not going to kill you probably, but it's going to be right of your life going on right there. Right, so we got the acceleration. Now we're ready to flip over to kinematic motion. Did you guys notice they never mentioned how much time to cover that runway distance, right? Which might be a hint. It's which kinematic equation says nothing about time. Is that the third one? Right, it goes like this. Final velocity squared equals initial velocity squared plus 2ax. You guys remember that one? Oh, yeah, I mean, you got the poster hanging over there. Right. Right. If it starts from rest, that guy's gone. All right. Now we know the minimum takeoff speed. That's gonna feed him right there. We know the acceleration. Just found that. And the question is, what's the minimum runway distance to make sure the plane's gonna take off? So let's plug in some values here. We're gonna plug in 70. Yeah, I'll just plug in numbers at this point. You can do variables if you want. This many meters per second, we got to pick up to. Don't forget to square that. Okay. Get from, right. Okay. Acceleration is 23.1 meters per second squared. And there's some runway distance. You got to figure out the runway distance. Okay. You guys see you can just take these two coefficients, divide them down. Get x equals. Right. All right. Going in for the finish. Now, guys, over this semester, or just in general, or many years of teaching, but one hang-up is, can you plug that correctly into your calculator? Can you communicate with your calculator? Can you do order of operations, group things correctly in parentheses? So I'm going to punch this in my calculator. you guys punch it in your calculator. Let's see if we're all getting the same number for how long does the runway have to be. All right, I got an answer on my calculator screen. Who knows? Who can tell me how long does that runway have to be? 135.7? Sounds right. Yeah, that's what I got too. Yeah. So 135.7 meters, right? And well, if you're all, how much precision can you have? You know, maybe around at one. If you said 136, that would be a really good answer too. All right. Yeah, that's what I'm getting to. Okay. And so if you plug that correctly into your calculator, you should be getting about that right there. Right, you guys good? Okay. If the runway is any shorter, the plane's not going to make it. If the runway is longer, then yeah, it'll be safe. It can be longer. That's all right. That's the minimum run. All right. All right. You guys ready for one more today? One more. So number 60. You guys see the sneaky one right in the middle? Skating. We got Joyce and Efwa are skating. Joyce pushes Efwa. Efwa has mass 40 kilograms. The push force is 5 newtons. What is Efwa's resulting acceleration? Of course, there's the question at face value, but I've got all my own side mini questions. So number 60, it's skating time. Joyce and Efwa. How about this? They said got massive. Let's get a couple of people. Right, they're pushing. What if they're different sizes? Right? Like I have say Joyce here and Efwa here, maybe something like that. Right? Now Efwa, mass of Efwa, you guys know is 40 kilograms because they told you that. Right? They're on skates, right? They're on skates. Right? Now, one thing I was thinking is when I saw this puzzle, take you guys through a few questions. How about this? Right? What if Joyce is bigger than Efwa? They never told you what the mass of Joyce is, but would that change the answer? If Joyce is bigger or smaller or the same size? Pushing with 5 newtons, right? Pushing with 5 newtons. Let's get some forces on the board. So I got this pushing force, F push is 5 newtons, right? What's the force back on Joyce? What if she's the same size? If she's the same size, is it also 5 newtons? Yeah. So I can say F push is 5 newtons, right? But what if she's bigger? I drew her a little bit bigger. Is it still 5 newtons? Yep. What if she's smaller? Is it still 5 newtons? Yep. Because that's what law of motion right there. Third law. You guys see two interacting people in this case? Yeah. Guys, this force is always equal and opposite. It doesn't matter if they're the same mass, different masses. That's Newton's third law. Now, there's some other forces too. We got this is not the scale, but you guys get the idea. Right? There's a weight, there's a normal force, weight, normal force. That's not really super relevant to this question though. Right? The other question I've been trying to get to is figure out, are they both on skates? Is just F1 on skates? Would that change the answer? Remember, we're trying to figure out what's the acceleration, right? Is that true? Right? Oh, what if see, like if Joyce is not wearing skates, what if she's just planted into the ground? She's not going to move. Isn't all the motion going into Efwa? Well, what if Joyce is on skates? Isn't she going to also push herself backward? Right? Which, if she pushes like sort of the same, I don't think it's all going to transfer into, say, Efwa's acceleration. Right? But here's the key, though. If you've established 5 newtons, then the answer is the same regardless. Right? If she's on skates, it's just probably more difficult to reach that 5 newtons versus if she's planted in the ground, it's probably easier to reach the 5 newtons. But once you have the 5 newtons established, the acceleration is the same regardless. Right? So can you guys just solve this very quickly with Newton's second law of motion? Net force on mass, and the net force is the pushing force, right? The verticals cancel out. So I got 5 Newton net force. I got 40 kilograms mass. Could that be like this many meters per second squared? Probably like that. All right. All right, guys, get there? Yeah, and that's gonna be our pause point today.